This afternoon, we have two sessions from Markus Wallerberger from Vienna here is going to tell us all about machine learning in his talk called Physics and the Machine. I would say the floor is yours.
All right. Very happy to be here. Very happy to be here. I mean, of course, I'm in Vienna, but it's been about 15 years since I've last been in this lecture hall, and it looks exactly as the 60s chic that I remember it. So it's very, very interesting that I have this opportunity to speak to you. And so maybe a few words about me and about what we're going to do here. And now, of course, this thing stops working because I think I have to do the got it, and now it works, right? Yes, perfect. So I was asked here to speak about machine learning. And so it's a huge and complex field. So there is a number of papers. The number of papers or preprints on the archive grows quite rapidly. And I'm not sure I like the analogy with Moore's law here, but it's fair to say that this field has been growing for quite some time. And so we felt here at the TU, there should be a basic introductory course of about 50 hours where we cover the bare minimum that one needs. So, and one of the participants of said course that is also here, I won't embarrass you, I say, is could you do a machine learning intro? And by the way, you have 45 minutes twice. So that's going to be a bit of a challenge because distilling that into that is a bit difficult, but I'll try. And the question really is how to set this up, how to tackle such a very complex field, and how to digest it into pieces that we can actually understand in that set amount of time. And here I took an inspiration. I was taking a couple of medicine classes, but found very quickly that it was not for me. But medicine takes a very systematic approach to breaking down this awesome machine, that awesome thing that we are, or that awesome thing that is life. And it does so by first breaking it down into its parts, what we call anatomy. We would say, okay, what is life? What are we? What is the brain? What is us made of at its basic level? And then there is a second part, physiology, where we examine how these parts work together to do its magic. And that's exactly what I am aiming to do. I'm aiming to expose the building blocks of machine learning here, the very basic ones, and then understand or how and why machine learning works. And then we're going to go to some applications. Right. So that's going to be part one. So I hope that's going to be cover that will keep us busy for this first session. The problem with that approach is, though, in medicine as in machine learning, if you only get that very high level overview, it's not really easy to translate that into something that you can use. So there's going to be a second part after the break where we're going to drill down to one specific topic in this machine learning thing. And we're going to do unsupervised learning, low-rank methods, and in particular, this thing called singular value decomposition, and try to understand how it works, because it's a very powerful technique, also very understandable to us physicists, that can be used in a variety of settings. And it lies at the core of many machine learning techniques. And then we're going to look at the Ising model and see what we can learn by applying that. There. Right. So that's the plan, 2 parts. So a couple of bookkeeping things. I am the kind of speaker who likes to get questions. So interrupt me anytime with a question. There is a microphone here. So just speak your mind. If you just want to throw it out there, I might repeat the question, so don't be shy. And since it's unlikely you already have questions, here's a question for you. What is machine learning? How would you define any idea? How would you, if you had to Okay, it's maybe unfair and mean of me to ask that question at the beginning, but if you were to give, doesn't have to be super exact, the definition of machine learning, anyone want to take a shot at that? Or something that comes to mind when you think of machine learning? Yes. Yeah, so a black box where you feed, I'll just repeat it, a black box where you feed in data and you get an answer. An excellent definition, I think. Really, really great, really gets to the core of it. Any other one? Anyone else want to take a shot at this? Yes. Yeah.
Many parameters to fit an arbitrary feature.
Right. Many parameters to fit an arbitrary feature. Anyone else? Also very good definition. It's very substantial part of machine.
I would say maybe that from my point of view, machine learning is something when you perform some kind of fit. So
yes,
you have a lot of parameters and you adapt it in order to make the better and better predictions. But of course, you cannot do it. You cannot do it deterministically because there is a lot of parameters, and you apply some algorithms that more or less similar to evolutions, maybe.
All right.
Maybe I describe only one part of machine learning.
A stochastic, a probabilistic way of fitting
yes.
an object. Very good. So it turns out the interesting thing was we didn't have a very hard time nailing the machine part. It's kind of hard to nail the learning part. It's a black box, it's fitting, it's probabilistic fitting, something comes out, it makes predictions, but what we actually mean by learning is maybe a little more fuzzy, right? So before we tackle that, maybe let's see what machine learning actually does. What is the constituents where it claims it can learn? And the anatomy of a machine learning is consisted of 4 parts. First, the data that you want to learn. So it works with data in some way. And ideally, you have lots of data. So machine learning works best when you have lots and lots of data. And what's even better is if you have a way to generate more data. So that's even better. And there we're in a lucky position in physics that often we do have that. We don't have like a set data set that Google has or something. We have a way to generate even more data. Then we have a second thing, and that is a model of our world or of the data. The data is a representation of something in the world, and the model is then a representation. The data is part of or samples part of the world, and the model is our understanding or representation of the world. And what sets machine learning apart is that these models are sort of general purpose. And then we have a third part, and that's the learning paradigm. And that is how we translate, that's this black box that you mentioned, how we translate, how we get the model and our data to match. How do we do that? And that's usually a fitting or an optimization problem. It's just 2 different words for the same thing. And then there's the fourth part, and that's how we make predictions from that. And that's also a special thing in machine learning. All right, so that's the 4 basic parts. Now sort of the taxonomy of it, these learning paradigms. Machine learning falls broadly into 3 categories: supervised learning, unsupervised learning, and reinforcement learning. So these slides will then be online, so you don't have to meticulously note everything down, but it's always good to note something down. All right. And these 3 things, the boundaries between them are not always sharp, but these 3 categories, I think, broadly are applicable. The first one is maybe the easiest to understand. It's supervised learning, and what we want the machine to do is to learn to give the correct answers to prompts we give it. So we give it a certain prompt, we confront it with a certain question, some data, and we show it for some of this data, we show it the answer, and we ask it to learn to predict or to give the correct answers to prompts we haven't given it. Unsupervised learning is at first a bit trickier to understand. It doesn't, and by supervised we mean we don't have an answer here. It's not, the data set is not, they're separated in questions and answers, but we have some data set and we want to discover structure in this data set. And now that seems a bit weird at first because it seems strange. We have to tell it somehow what that structure, for what structure it has to look for, because otherwise, how would it know what structure is? And that seems at first, when you encounter it, a bit counterintuitive. You might think, yeah, hang on, if I have to give it that structure, I don't need the machine learning algorithm. But it turns out that the structure we can give these algorithms is so general that it still can understand something from that data. And we will see in the second part, one of these structures is extremely powerful. And then there's the third paradigm, reinforcement learning. And here we have a way to interact with an environment. That's the way to generate new data in a way. So we have an agent that, so the machine tries to play a game, for instance, and interact with an environment. If we have like games, for instance, or there are interesting things where we have small bacteria that try to find food, you know, then finding a strategy, optimizing a strategy, how to navigate an environment, that's reinforcement learning. So these are the three paradigms: supervised, unsupervised, reinforcement. Now, again, I think these can be best understood in terms of data. So usually what we are working with is something called a design matrix or a data set. Now, it's just a spreadsheet of data. And each row is an observation. So it's a data point. It's one observation we make about the world. So we have a sequence of observations. And for each of these observations, we record information. So observables, if you want. Or in the machine learning terminology, we call them features. So each of these rows and columns is then the feature of some observation. All right, so let's do an example. For instance, say we have the periodic table of elements. Well, then each row would be an element, and each column would be some property of that element. Say its weight, its its specific weight, its electronic configuration, and so on and so on and so on. Or if we were to do, materials, we could do the same thing. If we want to do movies, we could have a movie for each row, and then whether it's a good one or not, or I don't know, and so on. All right. And here already we get that separation very nicely. So in unsupervised learning, we just take the data set as is. And take the full data set and just work with it. So this purple box. In supervised learning, we separate each data point into two parts, a question and an answer, right? So because remember, we want to learn the answer to the question. So that's the point, right? So we have what is called a label, which is the answer essentially. And then we have the other properties that the answer depends on, or that we think the answer depends on. So we sort of, that's a choice we are making. So say, for example, we might have as an answer here the boiling point of that element, if you have it in a molecular state. And then we had all the other properties, and we conjecture that in practice, the boiling point only depends on these properties. Now there's a choice here, and that's what I want to get out here. And the choice is, what are the independent features, so the question, and what are the dependent features, right? Okay. And then in reinforcement learning, we still take the full data set. There is no question and answer, but we have a way to generate new data. So we just add data as we interact with the environment. So this spreadsheet keeps expanding because we interact with our world. I talk to you guys, I get new information, you look confused or not confused, and that adds a data point here. Right. Okay, any questions so far?
For supervised learning. So, okay, I understand basically we give him some input and then we give him some kind of structure where it should make predictions. But is it then also possible, basically in this process, it just says like, okay, for element A, B, and C, like we find some kind of structure or anything, but like for B, it's not finding it? Or is it
Supervised or unsupervised?
Yes, for supervised.
Supervised. Well, in the simplest case, it would be, say, we would
Can be the answer no.
yes, I mean, the answer could be 1 or 0. For instance, there is something that these are usually represented as numbers.
Yes.
Sometimes, for instance, one of the simplest problems we ask are what's called classification problems. So the answer would be one of 2 categories, say it's you get an image, that's all these rows is an image, and the last column, which is the answer, would be 1 if it's a cat or 0 if it's not a cat. And we would ask the algorithm to figure that out for us. Yeah, very good question. Very pertinent, actually. All right, any other questions? No, it's either Y or X6. Depending on it's X6 if it's unsupervised, or it's Y if it's yeah, very, very good point. Yeah, it's not a division, sorry. It's either or.
Okay, maybe I have one question
Yes.
about unsupervised learning, because it's more or less clear what is supervised learning. Because, for example, if we have a lot of pictures with cat and dogs, we can split half of the pictures as a training. We can train our system on half of the pictures, and then we can use another half of the pictures to prove if have we trained it properly or not. For reinforcement learning, it's also more or less, so it's similar to something what happens in evolution, in real, in the nature. But what about unsupervised? So how it works? Because if you have some data set, what kind of structure you can find it, or probably you can maybe describe this data set by some minimal number of parameters, some best fit. But how can you avoid kind of overtraining? How to say?
It's an excellent question. So I will maybe skip a little bit ahead. So the unsupervised learning comes in 2 flavors, essentially. So let's maybe start with that. And that comes to the model of our data, because that is sort of what we're trying to get the data set, model the data set in some way. So for unsupervised learning, we have a couple of choices. 2 of the most popular are the following. The first one is that the data in our matrix is not actually all independent, right? So there is we don't need the full data matrix to understand our world. We only need a subset, right? So what would that mean? For instance, the simplest thing you can think of is take an image and compress it. So the compressed information would be that parameter here, or that vector here, and it would allow you to very good accuracy to reconstruct the full image. So that would be a way of unsupervised learning. In a sense, you can understand most of this form of unsupervised learning as a form of compression. That would be one. The second one is that you think there is a label there. There is an answer. I just don't know it. There is structure in the data. It clusters together in different answers. So there is some of that, for some of that materials, for instance, the answer would be 1, and for the others, it would be 2, and the others would be 3. I don't exactly know what 1, 2, and 3 means, but I know it groups into 3 groups. And that would be what clustering algorithms do, where we try to say, okay, there is some form of distance between data, and we try to find groups in the data. Also a very visual idea in a sense. So that's the second one, and there are more advanced ways to predict that. So basically it means always try to reconstruct either the full data set from a smaller set of parameters or find a hidden label that we didn't think was there. For supervised learning, we do have that label. And the simplest thing we can say is, okay, that means the label should be a function of the label, that is the answer should be a function of the parameters of our questions, our question. So we write down what's called a predictor, and we simply say, well, this thing is some function of these guys. And this we call the predicted label, because our model makes predictions about the world. This function might be something. Maybe linear, might be polynomial, might be neural network, might be something completely crazy. But what it always does is it depends on some parameters. For instance, if it's a linear thing, it might depend on the slope. If it's a neural network, there are some sorts of weights in there. Right, so that's the model. And for reinforcement learning, the thing is a little bit more complicated. It just says, well, I have given some observation. I find myself in a situation like this. I'm allowed to take an action. And I want to figure out which action to take in which situation. So that's the model I have of the world. Trying a strategy how to navigate the world would be the model there. All right, so that's the difference in models. So we have the difference in data sets and the difference in models. Yes? Yes, it would be like autonomous driving. It would be, for instance, autonomous driving would be, I'm confronted with a situation on the street. I get this as pixel on my screen. And my action is run over the pedestrian, don't run over the pedestrian, brake, steer, call Elon Musk, something, you know. That would be an example. Usually most reinforcement learning models are little. For instance, there's a fantastic paper called Run and Tumble Microswimmers I will maybe post the link here at the TU, actually done by Benedikt Hartl and coworkers. And they looked at bacteria and how they navigate, what is their ideal strategy. They can only do two things. They can either swim or they can rotate, and they have to find food. And sort of their policies, how is their optimal strategy, when should they turn and when should they swim to find the most food, given the observation of a food concentration. All right. Good. So now we have the data, we have the model. Now we need to understand what learning means, or training and learning means. Now we get to the heart of the matter. And that is, learning is simply adjusting our parameters until the model and the data match, right? So that would be our model. We would adjust our model of the world until it matches what we observe about the world. And it's the same for these things. We adjust such that these two match. Now the question now is, what does it mean that the two things match, right? And so one way to say it matches is to say it minimizes the mismatch. Okay, fine. So the thing that machine learning people like to say is it minimizes the risk or a cost function that we usually define as the average distance or squared distance in some norm that I'm not going to talk about between the answers that we give, the model gives, and the answers that are actually correct. And if we minimize that, we will give mostly correct answers because this difference is small. And for unsupervised learning, we do the same thing, but not just for the labels, for the answers, but for the full data set. We try to reconstruct the full data set, or we try to reconstruct, and I didn't write the cost function here, these hidden labels there. It's a bit more complicated, and I don't have time to get into it. Now, for reinforcement learning, it's a little different. What we have there is what is called a reward. And the reward tells us how good our action was. How good is the situation we find ourselves in. And we want to find ourselves in mostly good situations. So this is actually the first observation here. So that's a bit a bad number. But we say we add up the rewards of all of our observations with some decaying factor, because otherwise our training becomes very difficult. And we want to maximize this. We want to maximize the amount. For our swimmer model, it would be the amount of food we get, and so on. So that would be the idea. Right. So these are the three things we need. Then how do we actually match these two? So remember, we had the data, we had the model of our data, and we have some measure of when they match. So how do we get them to match? Well, what we do in practice is something called gradient descent. We want to minimize some function. And there are strategies to do that. And the simplest strategy is called gradient descent, where we simply walk around this very abstract landscape. So it's the strategy you heard maybe in your introductory computing class, where you simply follow the gradient of our cost function until we reach a minimum. Let me mention two things here. First, this gradient is fast to compute for neural networks on a GPU. And that is what historically has powered a lot of this artificial intelligence revolution. Because it used to be that very large networks are difficult to train because this gradient was very difficult to compute. And with GPUs, that became a lot easier. And also because there was a lot more data around. That was the other reason. Two more comments that I might not get into too much. We usually find a local minimum, but put a mental asterisk next to that, because it turns out that used to be the common wisdom, but it's not, almost not anymore. And that there is some alternatives that if you know Bayesian statistics, you can do an optimization of something called a posterior probability. I don't have time to get into this. Suffice it to say, this is much more expensive computationally, so it's seldom performed, though it's very powerful if you can perform it. All right, so that brings me to this overview. And this is really, now you understand machine learning, basically. You have a data set, you have something to learn, you have a model and a way to train. For supervised learning, our data set splits into questions and answers. We try to learn the answers. We have some function that predicts the answers, giving some questions, and we adjust the parameters such that we get mostly correct answers. So the number of the mismatch between predicted and actual answers becomes low. Unsupervised learning is we have a data set. We don't split it. We find structure in X in this design matrix, and we predict the whole data set by some function. And well, then the simplest case is we just say that we want all the items to be sort of reproduced. Then we have reinforcement learning, where we have a data set, a bunch of actions we can take, and a reward that is a goodness of our actions that we can get. We try to learn the best actions, and that we do by maximizing that reward we get. So, any questions there? Yes.
So you make a big difference between minimizing and maximizing, but isn't that kind of the same?
Yes.
Like either I minimize the Either I maximize how much food I get or I minimize how much I starve.
Yes, that
Okay.
usually you can, for instance, if you have your gradient descent algorithm, you can make a fancy thing and have it do, or just flip the reward and use your minimizer. Flip the sign of your reward and use a minimizer.
Yeah.
Yes.
So why did you decide to make a difference here then?
Because traditionally we do maximization for the reward. For the policy, we do something called gradient ascent then, rather than gradient descent. But it's tomatoes. In the end, the properties of these algorithms are very much the same. They're just mirror images of each other. I find it easier to think about it as a reward than a penalty, but not a huge issue in practice. All right, any other questions? Yes. The honest answer is, ideally, you have a little bit of idea what you want to get, if you want to get the answers or find some structure in the data. If you have no idea what's going on, so the question is which learning paradigm to choose. If you have the question is, what is your interest? If you have no idea, then unsupervised techniques are very nice, because you first look at your data set. I say, I have no idea. I assume some structure. Let's see what structure it finds. Let's just explore in a way. So then it's good to start with this. If you have specific answer in mind, say you want to predict whether it's a good clock or not. So you see, I have no idea what you guys do. Then you can say there is a goodness here of the clock as a label, and then you optimize for that, for instance. Yes. Yes. We will. It might be, for instance, say one option would be, say you measure some things and you want to understand if say you measure a bunch of quantities for your experiment. And what you want to understand if the quantities you measure are actually independent of each other, or if they are very strongly correlated, would be one idea. Because if they are very dependent on each other, they would strongly be linearly dependent, so they would be strongly compressible, which means that you get an idea, these two things always go together, or they seldom go together, or you really need the two things to understand your data. Another option would be, say you have different material properties and you want to say, do they fall into groups? Do our measurements fall into groups, for instance? That would be the other option. So these would be questions. And then you don't particularly know what you're looking for, right? Not necessarily. Yes.
So my question is, can I relate this to normal curve fitting, linear regression and non-linear regression?
Yes.
So like,
hold that thought for 5 minutes. Very good question. All right. Yes. 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 In principle, it's in the simplest case, it's a Markov decision process. Or yes. And it has, something like this. Yes. Yes, you can then use a pre-trained model, but it has a strategy and it refines the strategy as new data comes in. That's its big advantage. Very good point. Yes. There are models that are very difficult to optimize. Yes. I mean, there are models that are known to be very, very difficult to optimize. For instance, if you were to suppose you were to have your model be a quantum computer. So your label is predicted, so your Y is quantum computer output of some input. Now, if you were to do that, you know that classically it's near impossible to optimize this function, because quantum computers are very hard to optimize, because these things are very difficult to optimize generically. That would be one. There's actually, we will get briefly to that, probably we won't actually. Yes. 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 Yes, actually, usually you won't go exactly to the minimum. And we will come to that in a bit. Now, all right, maybe we'll move on. Actually, I had a joke here that I'm basically done at this point, but since I already said that you should hold on to these questions, it sort of fell flat. But anyway, so one little niggle that we had was, well, what I explained, isn't it basically things we already know? Isn't supervised learning basically function fitting? Isn't unsupervised learning basically a way to sketch the matrix? Isn't reinforcement learning basically control theory, optimal control theory? Isn't that? We have some cost function, we have some model, we fit it to the data. Isn't it basically that? And the truth is, yes, it is, in the sense that the anatomy is almost the same. But there are two things that I think set it apart to a degree. I mean, you could argue, okay, this is true, but I would say there are two things that set it apart. The first one is that we require of machine learning models that they generalize. So I will explain in a bit what that means. And the second thing is that we usually do not tailor our models that strongly to our application. That means we try to use quasi-universal or near-universal models that can, in principle, fit a broad variety of data. So let me explain what I mean by that. The first one is called generalization. So what we require of a model is that it doesn't just learn the data we give it to train, but it also generalizes to data it hasn't seen before. That's what we call learning, that we have learning is a transferable skill. If you have learned something, you can apply it to something else. So the easy version, basically everybody does in the machine learning community, which is we set aside some part of our data as sort of test set. We train only on part of that data that we didn't set aside, and then we check if the model also works on the data that we have set aside. Now, if we do that, that's sort of the easy version of generalization. I mean, everybody says, yeah, that's super important, and it is super important, but actually it's a bit of, that's the party line, but it's easy because, okay, it's ideally the data is very similar. The hard part comes when we try to get the model that is able to generalize to data it hasn't seen, or that is just similar, but not maybe exactly the same, maybe drawn from a different temperature or drawn from a different physical conditions. So that is very hard. So getting a model that can interpolate inside the data set to extrapolate is very, very difficult. And that would be what we get from AI. But in principle, we always require it to generalize to a certain degree. And the second secret sauce is that usually in machine learning, we don't use simple linear models. There's this famous saying by, I think it's John von Neumann, who said, with four parameters, I can fit an elephant. With 5, I can make it waggle its tail. Yes, so there's actually an animation on the internet which shows that. But anyway, we use often models with millions of parameters in machine learning. And we use a function remember, we can use any function here, and we use a function called a neural network, often, which is modeled on the brain, but it has a buttload of parameters. And in particular, it has a property called the universal approximate. It says what's called a universal approximator, which means that a neural network that is large enough can approximate any function. Any function. And in this article here, usually it was understood that the neural network needs to be very large to do that. But in this article here, actually Zhang and collaborators showed that the neural network doesn't need to be that large to actually do that. So these models can fit anything. However, these two properties are a bit weird. And to understand that, we need to talk a little bit about what these universal models can do. They can, in principle, learn anything. Anything. Any data we throw at it. But the question is, how can they understand anything if they can learn anything? And here is my analogy. I don't know, who of you learned a second language in school? Pretty much everybody. I used to ask who was American, but that was mean, I said. Yeah, anyway, whoever learned a second language, some of them actually do learn a second language at school. We used to learn words, and the way we had to learn words is word lists. We had essentially, here it's Latin, I think, but we had the English and the German words, and there were a couple of hundred words that you had to learn by heart, these pairs. This means that in English. I hated that. I positively hated. There was this way of cards that also didn't work, that you lose them. It would be pain, utter pain. So for a machine learning model, that would be easy peasy, because it would just, you would just feed that into a database. But the problem is, it would not be able to infer any other word from there. If we add a single additional word to that list, the machine learning model would not know what to do with it. It had learned that word list. In fact, we copied that word list into the model, but it learned that perfectly. When we ask it a word, it will give us the word from the word list. But say we want another word, how would it know? If it can learn anything, how would it choose? It has no bearings to understand what structure, what grammar is. We just gave it that word list. So the problem is that we have to constrain the model in some way to actually learn something. So learning is not just fitting, it's also constraining the model to make sure that we abstract from the data in some way to make inference about other data. Because if we never abstract, everything is just data points that are randomly associated. So that is the crucial thing. So, and that is the puzzle, isn't it? If we have machine learning and we have now these awesome models and we require it to generalize, how do we actually get them to generalize? And the answer to that comes in 2 slides, but in basically, there is a formalization of this concept called the bias variance trade-off, one of the foundational trade-offs of machine learning. And basically, these are fancy words for, the bias is a fancy word for the systematic error of our model. So the fundamental mismatch of our model and reality. And the variance is a measure of the statistical error, which is the uncertainty it has about the world. And now what the bias variance trade-off tells you is that for a given data set, that's very important, for a given data set, you can move between those things, but you can never, you can move between the things. For model complexity or given only for the data set, you cannot basically reduce both of them at the same time. It's very hard to do. So by increasing the power of the model, making it more powerful, making it able to learn more, it has lower bias, it can learn more things, but it has lower uncertainty, higher uncertainty about how to apply these things to new data. Conversely, if we constrain the model, we force it to abstract from the data, but its abstractions might be wrong. So we increase the mismatch between reality. It cannot learn everything anymore, but that what it can learn with higher confidence. So here's a plot from my slides, basically, from my lecture. So the way this then looks like this is here, I've plotted this as a graph. And so if we add power, if we add parameters to our model, then the bias drops. So we get closer to our truth, but the variance increases, which means this thing, we have less uncertainty, and the error we get in fitting is basically the sum of the two, more or less. So, oops, I'm sorry. And so we get an optimum here, essentially. So that's a fundamental trade-off. So it's clear if you think about this word list thing, but so you can formalize this trade-off. But yes, K is the number of essentially the number of parameters in our model, if you want. So if you have a neural network, for instance, so the simplest thing is, say you do a polynomial fit. You have your data and you try to fit the polynomial in there. Then K would be the degree of your polynomial. As you go to a low degree, you are here. So linear curve, you have a very good way to say, okay, this linear curve has pretty much exactly that slope. But the data might not be linear. Conversely, you might fit a 200 order polynomial in there. If you do, you get, it fits each data point really nicely. But woe is you if you ever go out and try to predict something. Then you have very low confidence for your prediction. So that's basically what this means. Very good question. Okay, I think I'm pretty much out of time. I will maybe say, how do we do this? I want to say two things actually. So I have to think a little bit how to do this. Let me go on a little bit, and then I figure it out in the way where to stop actually. So I want to state, and this is usually not mentioned, that the bias variance trade-off in a sense is a false dichotomy. And the reason for that is that we can always improve both. The variance we can always improve by adding more data. So if we have, that is why it is so nice to have lots of data available, because machine learning models get better as we add data without sacrificing bias. And that's very important. So in practice, that means that if we have a procedure to generate new data, say reinforcement learning, that's very nice, because it would pretty much guarantee that we lower the variance. We can also lower the bias by improving our knowledge of the thing, using another neural network, that is our brain, to improve our understanding of the data. And therefore, we can lower the bias for this specific thing because we can constrain the model to only those situations we know can happen. So that's important. Now, in the absence of that, we have one final trick up our sleeves. And that is the reason why machine learning models work, or one of the reasons why they work. And that is called regularization. So if we don't have the option to improve our knowledge, and if we don't have arbitrary amounts of data, we can still say, well, then we can, in principle, the parameters of a model can be anything. And they're usually very poorly determined. But we can say, well, we restrict our models to sensible parameter values, reasonable values. And in practice, one does this by adding a term to the cost function, because this is kind of a pain to enforce. This is more easy. But because these two, the relationship between the maximum parameter values and this parameter, so this penalizes large parameter values, this is not trivial, so one usually has to fiddle with lambda until it works. So there is a fancy name for it. It's called hyperparameter search, but it basically means fiddling with the regularization until the data looks nice. Now, regularization is a relatively weak way of constraining our model. And that means the following. If we apply vanilla machine learning techniques to physics problems, it tends to work well in situations where humans perform poorly, where standard algorithms also perform poorly, and where we are content with a relatively low accuracy. That means, for example, most machine learning practitioners are happy with a 95, 98% accuracy in classification problems. So that might be enough for us. But suppose you're at the LHC and you want to classify events as interesting or not interesting. Now the LHC or the CMS experiment and the Atlas experiment each have 40 million events per second coming in. Only about 100,000 are kept. If you have a 98% accuracy, that means you generate, if that accuracy divides evenly, 1 million uninteresting events per second. So that's not good. And the storage engineers in CERN won't be happy about that. So it depends on your application. There are situations where vanilla machine learning works well, the situations, but keep these three constraints in mind. All right. Now, there is ways around this. And that brings me to, I won't probably have time to get into all of these things. Let me just mention one. So there is a rich things interchange between physics and machine learning, where it is used, right? So physics informs machine learning in very interesting ways, where we improve the machine learning machinery. And machine learning informs physics, where we apply machine learning to physics problems. And there is an interchange in this region where we have quantum computing and quantum machine learning. So let me just mention one, because otherwise I'm out of time, mention one application of machine learning. I'm a material scientist, so it has to be something with material science, I'm sorry. It's machine learning potentials. And machine learning potentials means the potentials that your objects are moving in for many-body problems. So they're for molecular dynamics, that would be the atomic forces. So it's a classical simulation where you have the atoms moving around and they feel the forces of the other atoms. For band structure calculation, it's your electronic cone-sham potential that the other electrons produce, effective potential that your other electrons produce for your one electron. Now it turns out for humans, it's relatively difficult to write down good expressions for these potentials. Either they're very expensive to evaluate or they're quite inaccurate. That's good. It turns out though, it's hard to get the accuracy when you just do machine learning. So the most successful ways machine learning was used is to use simple models and reduce the number of features that we have already before. So a combination of unsupervised and supervised learning with simple models. And remember, the simple models have the fewer parameters, so they have the lower bias, the lower variance, excuse me. And this is state of the art. So if you do molecular dynamics or bench sector calculations, this has worked amazingly well. And it gets me to a statement that I might regret in 10 years, but it is that intensive quantities in the thermodynamic sense, like temperatures and potentials, tend to be easier to model. I don't know why. So for instance, the self-energies, things like that. So the most successful things I have seen in the physics community was models for intensive quantities. What? Temperature rather than temperature, pressure. In the thermodynamic sense, you know, extensive quantities would be things like entropy, things when you double the system, you have double the thing. Intensive quantities would be things that stay constant. If you have two things at a temperature, the temperature is the same. If you have twice the volume, it's twice. So that would be the difference. And for potentials, and so for instance, for potentials and charge, you know, that would be the conjugate pair. The potential is much easier. The charge would be harder to model. Why that is, I have no idea. All right. Okay, these three I will skip. I want to mention one thing very briefly. And that is, if I had given this talk in 2014, this bias variance trade-off thing would be the state of the art. We would say, okay, you shouldn't make your model too powerful. You shouldn't make it too less powerful, but it's a thing that you cannot get away from this trade-off. And somebody would have come to me and said, I have tried this out. I have tried by accident, say, to make a model with a bazillion parameters, and it still worked. And I don't understand why, because it shouldn't work. So why on earth did it work? And it turns out that since there is a seminal paper here in 2016 that tells us that, or that started the field that tells us that the bias variance trade-off is probably incomplete. We don't know why. We don't actually know why. But it's probably because we still restrict, we could use any parameters to fit our data, but we still find a solution where the parameters are sort of, the first solution we find are probably a solution where the parameter values are still reasonable. And that is why we find probably still a good solution. So what you shown here is that would be the curve that you saw earlier, you know, the error which goes from medium to a minimum, then to a high error, but then it goes back down again once you make the model parameters more and more model parameters. Why that happens, there is little knowledge, and we actually made use of that in a paper, but not understanding what actually goes on. All right, I have to stop here. I'm sorry I had to rush through the slides. All right, here's just an overview. The anatomy of machine learning is what we learn, the data, the model, and the way to match them. The physiology is that we have a near universal model and the way to generalize it. We always have to navigate the bias variance trade-off. And there are lots of clever applications, and where both machine learning informs physics and physics informs machine learning. And after the break, we're going to look at one of them.